So you've had time to flip back to 6.3. Recall the lecture 6.3 picture when we were defining the projection vector. And so here's kind of the motivation for today's lecture. This entire section is looking at one specific kind of problem. I've already talked to you a lot about how not every single system of equations has a solution. So they're not all consistent. There's some inconsistent solutions. But what happens if I want to figure out what is the closest thing to a solution that is not a solution? And what that ends up looking like is, say I'm trying to solve this. I have A times X is equal to B. And I know that this has no solution. Okay? So another word we use for that is what? Inconsistent. So I have an inconsistent system of equations represented with the matrix equation AX is equal to B. And so another way we could visualize that is, what this means is that there's no way I can take linear combinations of the columns of A such that that specific linear combination gives me B. Do you remember how we can write these matrix equations as vector equations? X1 times the first column plus X2 times the second column, and so on and so forth, depending on how big my matrix is. So if these are the same thing, and if this doesn't have a solution, okay, so if I take a linear combination of columns, and then all the possible linear combinations of the columns, that sure sounds a lot like span. I was joking with Samuel earlier about every time my span comes back as that one character that you can't kill even if you wanted it to. So we have the span of my columns, and that is how we define the column space. So this is all coming back. So the subspace I'm interested in is in the column space. And so basically, if I can't find the correct x values that tune it into the vector B, that simply means that I don't have something in this column space. And so let me make another picture that will look a lot like the one in 6.3. What?
So how long do you practice this picture?
You know, not as long, because I already did the practice for the other picture. And you'll find that it's going to be basically the same exact picture. So what I want you to do is, again, go back, put a thumb or a pencil, an extra pencil or something, in the 6.3 picture. Because I'm going to want you to flip back and forth between these and really see they're exactly the same thing. Okay? We're going to put down an anchor point here, like we did with the other diagram. We have a zero vector. And now, instead of calling the vector out here y, that vector is b. So now I have some vector out here, b, that I'm trying to get to. But I can't get to it using only the columns of A. So in 6.3, we called this subspace W in general, and now we have an application. So that specific subspace is the column space that we want to think of. Is B inside of my column space? No, that means that this has no solution. Okay, so this is all visually related to the equation. So, but what's the closest? So what is the closest thing in the column space I can do to get as close in distance-wise to that B? Well, what we found in 6.3 was just take that orthogonal projection down to the subspace and figure out where its shadow falls, basically, directly straight down. And then that vector that I then create, in this case, in 6.3, we called this the projection. But here, let's interpret this in light of our application to the column space. That's the vector that results when I multiply, I take my matrix A and I have some special x hat. And that special x hat is gonna, we'll talk more about this notation later and why we're using that. But for now, just trust. But this is still, if you want to think of this as the projection of B onto the column space of A, that is also correct. And then, what's special about this? Well, it's special because there are lots of other vectors I can access in the column space of A. For example, I could access this vector right here. I could access this vector AX1, say. So I have some vector, x. And if I do that, but then let's see, how far is this distance to my B? That's definitely a greater distance away than my AX hat. And what if I chose maybe a point over here? If I had a point over here, A, and then I tried some other vector, x2 maybe. Well, what about its distance to B? Now obviously it looks shorter because it's 3D, but that you have to angle. There's a higher angle. And so what we're going to find is that this specific vector, which coincides with that projection vector, is special because of all of the possible members of my column space. This specific vector is the one that gets me the closest in distance to B, making it, in application, the most accurate approximation of the solution, even though we can't actually solve this equation. So we can't actually solve this because it has no solution. And so what we do is we cast it down and view its projection in column space, and we solve for that specific vector, the projection. And that projection is not the true solution, but for all intents and purposes, if I'm restricted to viewing only the columns of A, then that's the closest thing we have to the solution. And so this is going to be our best approximation. So let's summarize a few things here. Some observations. Firstly, B is not in the column space of A. Visually, and also by just logic of this statement here, AX equals B has no solution. Secondly, note that A times this x hat is actually just coinciding with the projection onto the subspace, call A, from the vector B. And this is a great point where if you saved your location in your notes to 6.3, you can check that for yourself. Make sure that you can really understand how we've just relabeled a concept that we've already studied. And so, what does this mean? Well, what this means is now visually, suppose I have just my AX hat. Is it possible for me to access AX hat using only vectors from the column space? Yes, because I'm actually now in the subspace. And so, if I rewrite the equation with AX hat, AX equals X hat. This is consistent. So I can actually figure out that solution. And now obviously you're looking at that and you're thinking, well, this just then use the x hat as your solution. And that is correct. I'll write down this little explanation here. The vector B is closest to A times this x hat, which coincides again with our projection vector. Does the formula for projection change by chance just because we've decided to apply it? No. So do you already technically know how to do this entire section before today? Yes. But I'm here to help reframe the application so that you have a more efficient mental patchwork to work with here. It's orthogonal projection. It's orthogonal projection onto the column space of A. That is, so what's another way of thinking about that that's the same? That is, the vector x hat, is the closest possible, approximation of the solution for AX, the original matrix equation, AX equals B. The vector B is closest to the vector AX hat because it's the orthogonal projection. So that vector x hat we're very interested in because that's going to be the best approximation for what the solution should be in quotes, because technically there is no solution. Okay, do we have questions about the picture and how it relates to the statement up top here? Questions about what we really mean by shortest distance. Is the distance been drawn in here pretty visually clear enough? Mm-hmm. Do we have a good visual intuition of if I chose any point at random inside of this column space, the only one that's closest is the one that just happens to coincide with the projection? And since that's always the case, then we can start thinking about it that way. And then the practical ramification that we'll explore with the least squares method is this very statement that, okay, sure, I can't actually solve that, but let me approximate it. Jessica?
For the equation, is it xn a(n) or xn a2?
It should be AN.
Oh, yeah, no, thank you for catching that. I don't know why I put a 2 there.
Okay, I just wanted to make sure. Thank you.
Okay. So let me give a definition. I think I'll keep this picture up. Question? The reason I spend a lot of time making sure you understand the concept in words is because the math notation is going to look a lot more obscure than it makes the concept seem. And so I want to just basically positively gaslight you into understanding the overall section so that when you see stuff that doesn't make sense, you tell your brain, haha, I still understand it anyway. And then with hindsight, when you're actually reviewing the section and doing your problems, the funny thing about that is even though it started as positive gaslighting, it becomes actual understanding. When I was self-studying through some graduate level topology, what I had to do was convince myself and tell myself that I understood material that I didn't actually understand. And then approximately 3 sections later, I would unironically understand the stuff 3 sections ago that I told myself I understood that I didn't understand. I can't tell you how that happens. I also can't tell you how that works. So don't feel bad if you feel like you're faking it right now, or for that matter, in any math lecture, because that is basically how learning math works at the college level. You don't understand it, you tell yourself you do, you move on, and then you come back later and realize that you actually did understand it somehow, in some way, you just don't know how. Or you're a super genius child and you can understand everything, but that is not me. my least squares solution of a matrix AX equals B is in vector, and then this is our x hat that we've been talking about, in Rn. Such that, now here's the jargon, but trust me, you already know this. The distance between the vector B and AX hat is less than or equal to the distance between the vector B and some other vector AX for all of those possible x values in Rn. Okay? Think about these as distances. What each of those are, this dotted line right here, that is the distance between B and AX hat. Okay? That's what this distance is, here down to there. Whereas this really long diagonal distance would be, for example, the distance between the vector B minus AX1. So that would be like this distance. And so all this definition is saying is, if I were to take all of the possible distances inside of my column space, I specifically want the one that has the shortest distance to my B. That's a fancy way and a roundabout way of simply saying this is the closest approximation of the vector B. So as long as you understand that we are trying to minimize the distance between the subspace and my vector B, or if you want to think about it in terms of best possible approximation, they're all equivalent and they're all fine. Okay, so pick one that makes the most sense and stick with it. And when you go to the problem. So here's our theorem. The set of least squares solutions of AX is equal to B coincides, it's a fun word, with the non-empty set of solutions, the non-empty set of solutions of the normal equations, Now this is bad math form at the grad level, but your undergrads, it won't kill anybody. I'm going to define normal equations in the statement of the theorem. AT times A times X is equal to AT times the vector B. Gee, that's a massive font. That could not be in the least important whatsoever to this class or to the exam. You won't need to know that. Why else would I put a box around it? Certainly, I am not attempting to direct your attention to the very large, oversized formula on the whiteboard. Gee, I don't think you should handwrite that in your notes. I don't think you need that in your notes. If anything, it's probably irrelevant.
Do we have to box it as well? Yeah.
No, but you have to underline.
Hey,
Everyone boxed.
what? Really think about this for a second. Compare it visually to just my AX equals B. What have I modified? How have I modified just an original AX equals B?
You added the transpose of A to both of them.
Yeah, I'm left multiplying the transpose of A on both sides. Because if I did it to only one side, then I fundamentally changed the entire equation, so that's not quite right. But yes, all I've done is I've taken my original AX is equal to B, but then left multiplied by A transpose. Now, A transpose times A, fun fact, is just a matrix. And then A transpose times B is going to spit out some sort of a vector. So, long story short, you really do just have another matrix equation. It's just how do I know what to use? Well, I don't know. AT times A for your new matrix, and then spit B through your transpose for the other one. Okay? So, this is going to spit out all of the solution. So another way you can think about it is what's an alternative way I could have figured out this x hat? Well, an alternative way you could have gotten that is because x hat is the solution to this equation. Okay, so it's just recasting it as a computational formula. And the computational formula is the one that we're going to practice using. Okay? So, do we have the formula written down?
Maybe.
With the box.
Perchance.
Okay. I'm asking not rhetorically because I want to erase this and put the question. Do we have the formula written down? Okay. Mr. Patchen,
Yeah,
what's my formula?
your formula is matrix A transpose times A times our x vector is equal to matrix A transpose times our b vector.
No, Valley. What is our formula?
A transpose times matrix A times the x vector equals A transpose times the b vector.
Victory, what is our formula?
We have A transpose A times the x vector times A transpose times the b vector.
Ms. Rowland, what is our formula?
AT times A vector x equals AT times vector t.
Okay, we're going to find a least squares solution. Notice I can't say we're finding the solution because, fun fact, the system I'm going to give you is inconsistent. Okay, so obviously it has no solutions, but we're looking for a least squares solution, which will exist, of the inconsistent system. Oh, I can fit that. Inconsistent system. Wait, hold on. Inconsistent system. What? Least square solution of an inconsistent system. Wow. Make it a tongue twister. AX is equal to B. Can we solve AX equals B?
No.
No, why not?
It's inconsistent.
It's inconsistent. Oh no. What do we do? What are we ever going to do? Okay. Don't do that. A is equal to 401, 021, and B is equal to 2011. That, my friends, is an inconsistent system. You already can visualize, if I try to augment that, I'm going to have a square augmented matrix. That should already screen trouble, because if you're augmenting a matrix that's going to have solutions, at a minimum, you should not have it be a completely square thing, because that means that entire bottom row, if you try to row reduce down, you have issues. So this is not going to have any solutions. It'll break if you try to do that. So we look for the least squares. So here, I like these little steps. These are pretty fun. Step 1. Agnel, what was the formula?
A transpose A x vector equals A transpose times B vector.
Cool. So let's take this one chunk at a time. That left side is A transpose times A, right?
Yep.
So A transpose times A. Well, remember, to build a transpose, all I'm doing is I'm swapping out all of the columns and making the columns rows. So here's my first column, 401. So instead of writing 401 as a column, I'll write it as the first row. 401, like that. Okay, what's the second row? 021. Okay, so that's my A transpose. The order matters, by the way. Do not put it in the opposite, in the reverse order. The order matters. So A transpose A. So A, I just copy and paste my A. 401, 021. That's going to equal something. Do we remember how to... Let's also think about this. What are the dimensions here?
2 by 3.
Okay, so this is a 2 by 3. What are the dimensions here?
3 by 2.
So what should the output be?
2 by 2.
So I'm expecting a 2 by 2 with 4 entries. So I'll work through this one multiplication with you for practice, okay? I'm going to look for the entry specifically in row 1, column 1. Everyone got that? Row 1, column 1. So when I come to my product, I'm going to take row 1, column 1. 4 times 4 is 16, 0, and 1. Now, if I go for row 1, column 2,
Would be 1.
row 1, column 2. 4 times 0, 0 times 2, nice and easy, and then just 1 times 1.
0 plus 0 plus 1.
Okay, Danny, what's going to go in, actually, here about this. Can you give me the row and column for this entry?
It's going to be the bottom row and the front column.
Okay, and then Sam Vargas, give me the product.
1. So that'll be 4 times 0, 0, 0 times 2, 0, 1 times 1, 1.
Beautiful. Yes, everyone got that? Okay, everyone take 30 seconds, figure out the last one, and then shout it out when you got it. Thank you.
He gave me 30 seconds.
30 seconds.
You know, 30 seconds
said-
was the overall boundary of time, but being able to do it is... Okay? Yes? Super mindful, super demure. Okay. I still to this day don't know what that word means.
He gets
Natalie, what was our formula?
Matrix A transpose times matrix A plus vector x equals matrix A transpose times.
Beautiful. Do we have the A transpose A piece then? Okay, what's the piece we don't have? Well, the right side of the equation, right? What is the other vector? What is my A transpose times my vector B? Right? What? That's so crazy. I actually already know what this one is because I just did it. So I can copy paste that. And then my vector B, don't have to solve for that because it was given to me. This is dimensions are 2 by 3. And then what are the dimensions of this?
2 by 1.
What are the dimensions of this? 3 by 1. It's rows by columns. 3 by 1. So what's the output going to be?
2 by 1.
2 by 1 column vector. Okay? Okay. Well, you guys know how to do this. What's the top entry? 19. And what's the bottom entry?
11.
Yeah, we have 0, 0, 11. 19, 11. Okay. Let's see. Axel, what's the formula?
AT times A times vector x, and the x vector equals 18 times the vector b.
Okay, cool. So we kind of have the important parts of this thing. So my ATA is this 17, 1, 1, 5 times my vector x is equal to ATB, which is my 19, 11. Yeah? Which E? That's just the system of equations. This is consistent. And you can solve that. So, let's see. Here's what I'm going to do. I'm going to erase the work that we've done, and then I want you all to get a fresh piece of paper, rewrite the problem on top of your fresh piece of paper, reproduce the solution, and your exit ticket in this last, you'll get out early probably, if you've been paying attention. So if you finish early, you can leave early. Just come bring me your solution, okay? So I'm gonna erase this. And you're gonna show me a fresh, new page of paper with the problem and a full solution. Okay? Practice this. Take the time to practice this. And obviously, if you have questions, I'll be walking in between the rows to help you guys out, okay?